طيب, inshallah today I will end up with the topic isentropic efficiency. We talk about isentropic efficiency for turbine. We said this performance parameter applies to the adiabatic steady flow device for turbine. We have learned how to calculate the isentropic efficiency for turbine. Then we move to the case of compressor or pump, and we learned how to calculate the isentropic efficiency for compressor or pump. In any case, it is a ratio between the actual work divided by the reversible or the isentropic work in this case. Inshallah, today we'll end up with this topic, isentropic efficiency, but we will be talking, inshallah, about the nozzle, isentropic efficiency of nozzle. Nozzle it can apply also for diffuser, but we'll limit the case to the case of nozzle. Nozzle has different applications, as you know, in turbine working as a fixed blade. So nozzle, for the nozzle, as you know, the main function of the nozzle is just to accelerate the flow. And it is working as fixed blade in case of turbine. So we have a flow. This flow actually is coming from the big cross-sectional area. And the area in the flow direction is reduced. Nozzle is a steady flow device, so mass flow rate, which is density multiplied by area by velocity. This mass flow rate is constant at any cross section. Okay, so when we move from one cross section to another and the area is reduced for the same mass flow rate, so in this case the velocity should be increased in this case. And we said, based on Euler equation, relates the pressure with velocity. Delta V is equal to minus rho V delta V. We have negative sign between pressure and the velocity. That means if the velocity is increasing, that means the pressure actually, in this case, B2 should be reduced in this case compared to the pressure B1 at the inlet section. So B2 is less than B1 in this case. And the main function of the nozzle is to have what? Is to raise the velocity or to accelerate the flow in this case. So in case when we have a turbine or something, we have just drawn this many times. We have buckets here. Blade actually an impeller with blade, so the flow actually is leaving with high jet velocity, so it can hit the blade. Then in this case we can have the shaft rotating in this case, and we have shaft bar in case of turbine. To evaluate the isentropic efficiency of the nozzle, the isentropic efficiency is the ratio between what, Shabab? What we need from this nozzle is what? Kinetic energy, is it?
Yes.
We need to accelerate the flow. So it is the ratio between the kinetic energy, the actual kinetic energy, and the kinetic energy actually if this process of expansion from high pressure to low pressure is isentropic. We call it actually S as we used to do. So it is the ratio between the kinetic energy, actual kinetic energy, when we have some losses within this nozzle, some friction losses or something. In most of the cases, this nozzle has a small dimension. So small dimension actually, and with this very high flow velocity. So in this case, actually, there is no residence time actually to have heat transfer. So in this case, the heat transfer in most of the application for nozzle and diffuser, we don't have heat transfer due to the small dimension of the nozzle in this case. So we don't have heat transfer. But while the flow is going with this actually very high velocity, we expect here to have some friction to the flow. And in this case, the actual velocity, the flow will be leaving with the actual velocity, based on which you can calculate the actual kinetic energy. And if we assume actually we don't have any losses, that means the actual exit velocity will be higher in this case. And in this case, the kinetic energy, we call it the isentropic kinetic energy at the exit, or the maximum kinetic energy can be obtained in this case if the process of expansion is isentropic. But if we look at the Bollier diagram for this expansion process inside the nozzle, from high pressure B1 to a low pressure B2, as we said, the pressure is reduced because the velocity is increased in this case. But if the flow is coming to the nozzle at state number 1, if this expansion process is isentropic, we don't have any kind of losses, then in this case, the entropy will be constant and the flow will be leaving at point 2s. The process from 1 to 2s, so process from 1 to 2s, this is isentropic process, in which actually we have S1 is the same as S2, or we can say actually the change of entropy delta S is equal to 0 in this case. Okay, but this is in case when we have isentropic flow, we don't have any kind of losses. And in this case, we don't have entropy generation because entropy is generated within the system due to the losses within the system. As long as the process is isentropic, reversible, we don't have any kind of losses. So in this case, the entropy will be remaining constant, and we don't have any kind of losses. Type this expansion for the process from 1 to 2s. This expansion should give us indication about what? About what? Isentropic kinetic energy. So the kinetic energy in case when we have isentropic process, which should result actually in maximum exit velocity in this case. But in case if this process actually is actual, so we have some losses, so some entropy will be generated within the system. Entropy generation, that means we have a change in entropy in this case. And we should have in this case, if the system is adiabatic, if you recall actually at the beginning of this chapter, we said if the system is adiabatic, in this case actually delta S should always be a positive value, okay? So if the system is adiabatic, delta S should be positive in this case. And in this case, we should have some change of entropy delta S in this case. And at this point, the flow will be leaving at point 2A, which is the actual exit point in this case. And this difference, 1 minus H1 minus H2 actual, this difference should give us indication about the actual kinetic energy at the exit section between the inlet and the outlet section in this case. Okay, so that should equal to the isentropic efficiency of the nozzle, which is kinetic energy is equal to half V squared. If it is leaving at the actual point 2A, so it will equal to V2 actual divided by V2 actual squared divided by V2S squared. As we have the kinetic energy is equal to what? Is equal to half multiplied by V squared. Kinetic energy is function of V squared. So the isentropic efficiency of the nozzle will equal to V2 actual squared divided by V2S in this case. And V2S is called as maximum or isentropic exit velocity. So if he asked you in any problem, if I asked you in any problem, calculate the maximum exit velocity, that means actually I need to calculate V2S, which is actually as the isentropic exit condition in this case. Okay, so maximum exit velocity, maximum or isentropic exit velocity, we call it actually as V2S when the process actually is isentropic in this case. But if we apply شباب the first law of thermodynamics for this nozzle, if you recall actually the first law of thermodynamics for a nozzle, we don't have heat transfer, we don't have work, and we resulted that actually H1 minus H2 for a nozzle, enthalpy at the exit minus enthalpy at the outlet should equal to V2 squared minus V1 squared divided by 2, and we said we have to divide by 10 to the power 3, so that actually the whole term is in kilojoule per kilogram. In case of nozzle, the inlet velocity is much less than the exit velocity. So in this case, usually we neglect the inlet velocity with respect actually in comparison to the exit velocity. Okay, and in this case, if V1 is neglected in this case, that means H1 minus H2 should equal to V2 squared divided by 2, and don't forget to divide by 10 to the power 3. If we are talking about actual exit point, this will be H1 minus H2 actual equal to V2 actual squared divided by 2. If we are talking about the isentropic process from 1 to 2s, then in this case we can apply the same equation, H1 minus H2s will equal to V2s squared divided by 2. Okay, but based on this issue, can we just get the ratio V2 actual over V2s, V2 actual squared divided by V2 isentropic squared, and redefine the isentropic efficiency of the nozzle, which is V2 actual squared divided by V2 isentropic squared. But get the ratio here, V2 actual divided by V2 isentropic, so this term will go with this term, and that should equal to the ratio H1 minus H2 actual divided by H1 minus H2 isentropic in this case. But this formula, shabab, is only applied if what? If the inlet velocity is what? Is equal to 0. So the isentropic efficiency of the nozzle, this is the definition, the mean definition of the isentropic efficiency of the nozzle. طيب, based on the first law equation, this equation which we have developed in chapter 5, we can get those two relations for the actual and isentropic process. And we can get the ratio V2 actual square divided by V2 isentropic square. It can equal to actually H1 minus H2 actual divided by H1 minus H2S. But this equation is developed based on what? Based on neglecting the inlet velocity with respect to actually to the exit velocity. So if V1 is neglected, then in this case we can get those two relations, substitute here, and in this case only we can say the isentropic efficiency of the nozzle is also the ratio of the change of enthalpy in this case. Okay, Shabab? Is it okay? Okay, so if this one, V1 is not neglected, then in this case we cannot define the isentropic efficiency in terms of the enthalpy. We can just define it in terms of the velocity. And this velocity, Shabab, is called as the maximum velocity when the process of expansion is isentropic from 1 to 2s. Okay? Like, let's see here, let's see this example. Okay? Like in this example, he said we have air enter. So air, Shabab, is an ideal gas. So when you see any gas, then I have to keep in mind that I will be using the ideal gas equation of state, and I have constant specific heat analysis or variable specific heat analysis. And as I told you, in any problem, I will tell you which procedure you have to follow. Last time we solved a problem for the isentropic efficiency for the compressor using actually the exact analysis. Today, inshallah, let's solve this problem with the approximate analysis. So in this case, he said the air, which is the working fluid. I have to define in any problem the working fluid first. So we have air at 200 kilopascal and 950 Kelvin, enter an adiabatic nozzle. So adiabatic, so I have to write down, translate this, heat transfer is 0, and actually in this case, the device is a nozzle, which is a steady flow device, open system. So this is the nozzle. The flow is coming at pressure B1 is equal to 200 kilopascal, and temperature T1 is equal to 950 degrees C. And the working fluid is air. This is expanding inside this nozzle and leaving at pressure B2 is equal to 80 kilopascal. Okay, the isentropic efficiency. So, Shabab, it is the same problem like what we have considered actually in chapter 5. But what is added here, he just give me another parameter, which is the isentropic efficiency of the nozzle. He said the isentropic efficiency is equal to 0.92. Okay. And we need to calculate the maximum possible exit velocity. So what is it, Shabab? The maximum velocity is what? V2 actual or V2S?
2S.
V2S, which is the isentropic exit velocity. And we need also to calculate the actual exit temperature, T2 actual. And also we need to calculate the actual exit velocity, V2 actual in this case. So if, Shabab, the isentropic efficiency is given in any problem, I have to just write it down, given or required. Just have to write down the definition of the isentropic efficiency. Here we are talking about nozzle, so the isentropic efficiency of the nozzle, V2 actual square, divided by V2S square. And in this problem, he said the flow enter an adiabatic nozzle in the first line at low velocity. Low velocity, that means actually the velocity V1 is neglected. So V1 is equal to 0. So in this case, we can add this definition as well. H1 minus H2 actual divided by H1 minus H2S. In this problem, if you have to calculate H1, H2 actual, H1, H2S, in this case, if I'm following the exact analysis, I will be using the tables. For air, it is table A17. Okay? To get the value of the isentropic efficiency difference for the isentropic process from 1 to 2, S1 is the same as S2, like what we have solved last time. At the temperature, air at the temperature T1, I got H1 and I got B relative in table A17, then I calculate B relative 2 and went back to table A17, then I calculate H2S using the tables. Okay? But this is the exact analysis approach. I will be using table A17 to calculate H1 and H2S. But here I'm following actually the approximate analysis. Approximate analysis in which actually, or the constant specific heat analysis, in which we can substitute this delta H will equal to what, if you have CB average multiplied by T1 minus T2S, which is H1 T2 actual. Okay, divided by H1 minus H2S, which is CB average multiplied by T1 minus T2S. This CB average is calculated at the average temperature between the inlet and the isentropic exit. And this is between the inlet and the actual exit. Usually we don't have significant difference, so that we can neglect this value. So it will be the efficiency will equal to T1 minus T2 actual divided by T1 minus T2S. But for the isentropic process from 1 to 2S, S1 is the same as S2S, or delta S is equal to 0. Following the approximate analysis, we have developed those relations for ideal gas. I have to get back to those relations for an isentropic process. Following the approximate analysis, we can use this relation directly. We can say T2S divided by T1 will be the ratio between B2S divided by B1 to the power K minus 1 over K minus 1 over K. We have T1, which is 950. This is degree C, so it will be plus 273. I need to calculate T2S. I have B2 is equal to 80 kilopascal. B1 is equal to 200 kilopascal. And the value of K is calculated from where? K is calculated at the average temperature. But actually we have the inlet temperature and we don't have the outlet. If it is in your exam, I will just tell you just use the inlet temperature to be the average temperature. So the inlet temperature is 950. In this solution of this problem, we just assume here that the average temperature is equal to 800. And then I will go to table A to B. Then I can get CB average will equal to 1.009. And also I can get from table A to B for air, I can get the value of a specific heat ratio, K. K will equal to, let me check those values here. So at 800 CB, so it is from here. So CB is 1.099 and the specific heat ratio 1.354. Okay, so the value of average specific heat, if it is in your exam, I will just, because we don't have the exit temperature, I will ask you to get those values, the specific heat ratio and CB average at the inlet temperature. In this problem, we just assume the average temperature is equal to 800. We would go to table A to B, get CB average and the value of P. Then we have the value of P, 1.354. Then we can substitute here to get the isentropic exit temperature, which is T2S. We have T1, which is 950, and this is T1 is 950. T2 actual we need to calculate, and if you calculate T2S using this relation, the value of T2S you calculate, it will equal to 748. Okay, then we can calculate the actual, this is T2S. Okay, so based on the definition of the isentropic efficiency of the nozzle, we can calculate in this case the actual exit temperature based on the approximate analysis. Okay, so if you substitute here the isentropic efficiency of the nozzle is equal to 0.92, then we can substitute here to solve for T2 actual. If you calculate this, you will find the value of T2 actual is equal to 764 kilo. Are you following this, Shabab? Following or not?
Yes, following.
So this is the definition of the isentropic efficiency. Equal to 0.92, this is given. V2 actual divided by V2S, this is all squared. Equal to H1 minus H2 actual divided by H1 minus H2S. H1 following the variable specific heat will equal to CV delta T. H1 minus H2S will equal to CV delta T. Can just remove CV, and then it will be T1 minus T2 actual divided by T1 minus T2S. To calculate T2S, which is the isentropic exit condition following the approximate analysis, T2S over T1 will equal to B2 divided by B1 to the power K minus 1 over K. We have T1, B1 and B2, then we can solve for T2. And the value of T is from table A to B and CB. Solve for T2S, you can find this value equal to 740. Just substitute here, then we can solve for the actual exit temperature in this case. طيب, how we can calculate the maximum exit velocity? We said H1, applying actually the first law of thermodynamics for the isentropic process, H1 minus H2S will equal to V2S squared divided by 2, and we have to divide also by 10 to the power 3. Okay, this is the maximum exit velocity, and following the approximate analysis, H1 minus H2S will equal to Cv average multiplied by T1 minus T2S. Cv average, we got this at the average temperature from table A to B, or the given temperature in this case. We have T1 and you have calculated T2S, then we can get actually this value. This value is 1.099. We have those values, then we can solve actually for V2S, which is the maximum exit velocity. V2S will equal to 666 meters per second. Okay, but we need to calculate also for the actual exit velocity. We have the isentropic efficiency is 0.92. We solve it for the isentropic velocity here, which we have calculated from this equation. Then we can just substitute here to calculate the actual exit velocity. Actual exit velocity will equal to 639 meters per second. Okay, so شباب, it is the same problem like what we have learned to solve in chapter 4. We have nozzle and we apply the first law of thermodynamics to relate the change of enthalpy with the kinetic energy. And what is added here actually is the definition of the isentropic efficiency of the process, which is the ratio of the kinetic energy. And in case if we neglected the inlet velocity, it can be also the ratio of the change of enthalpy. But the change of enthalpy, we have either constant specific heat approach or variable specific heat. Variable specific heat, I can replace it with Cv multiplied by delta T, and then we can solve for the equation.